Welcome to my 34th tutoring session in A-level chemistry. In this video, I'll talk about polar and non-polar molecules. Now, polarity is seen in heteroatomic molecules. Now, what is a heteroatomic molecule? A heteroatomic molecule is one where you find the bonding between two different atoms that are not identical. Like in case of hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide molecules, you find that the atoms held together by covalent bond are totally different. So polarity is generally seen in heteroatomic molecules where the bonding is between different atoms. And as a result of this, you find unequal sharing of electron pair in the molecule. That is in case of heteroatomic molecules with partial positive and negative charge. Let me explain this concept with respect to hydrogen chloride molecule. Now, hydrogen chloride is a heteroatomic molecule where you find the hydrogen atom and the chlorine atom are held together by covalent bond that is shown by a solid line joining the hydrogen atom and the chlorine atom. So as we all know, a covalent bond is formed by mutual sharing of pair of electron. But in case of hydrogen chloride molecule, you find there is unequal sharing of electron pair between the hydrogen atom and the chlorine atom. And the shared pair of bonding electron is more towards the chlorine atom, or it is very close to the chlorine atom. And this is shown by arrowhead pointing towards the chlorine atom. Now the chlorine atom attracts or pulls the shared pair of bonding electrons closer to itself, and this leads to development of a partial negative charge in the chlorine atom. That is to say, the chlorine atom gains a partial negative charge while the hydrogen atom gains a partial positive charge. So what is making the chlorine atom to attract or pull the shared pair of bonding electrons closer to itself? So the answer lies in the electronegativity of chlorine atom. Now electronegativity value of chlorine is 3.1 while the electronegativity value of hydrogen is 2.1 on the Linus Pauling electronegativity scale. So chlorine atom is more electronegative than hydrogen atom, and as a result, it pulls or attracts the shared pair of bonding electrons closer to itself. And this leads to development of partial negative charge in the chlorine atom and a partial positive charge in the hydrogen atom. And this is shown by Greek symbol delta plus and delta minus. That is partial positive and partial negative charge. So one can predict the polarity of a molecule based on the electronegativity difference between the bonded atoms in that particular molecule. So whenever the electronegativity difference between the atoms held together by a covalent bond is greater than 0.5, you can take it for granted it will be a polar covalent bond and the molecule will be polar in nature. Because whenever you find a polar covalent bond, there will be a partial positive and partial negative charge. So one can predict the polarity of a molecule based on the electronegativity difference between the atoms held together by covalent bond in that particular molecule. So as an outcome of this, you will find unsymmetrical electron cloud with partial positive and partial negative charge. You will find polarization of the electron cloud where the electron density is more towards the more electronegative atom, in this case chlorine atom. And there is an uneven distribution of negatively charged electrons in the molecule. And as a result, you find partial positive and partial negative charge in the molecule. So where the electron density, that is the electron density is more towards the electronegative atom, that is the chlorine atom in case of hydrogen chloride molecule. So now you have hydrogen chloride molecule with a positive end and a negative end. It has a dipole with a polar covalent bond. And this is indicated by arrow. It's a special arrow where you find the crossed end and a arrow end. So here the crossed end will be the positive end of the molecule and the arrow end will be the negative end of the molecule. So these are some of the highlighting features of a polar molecule and the reason for polarity. Now what about the non-polar molecule? Now non-polarity is seen in homoatomic molecules like hydrogen molecule, nitrogen molecule, oxygen molecule, fluorine, chlorine, bromine, and iodine molecule. Now even alkanes are also non-polar in nature. Now here you can consider alkanes as an exception. Now why alkane with carbon and hydrogen atom are non-polar in nature? As we have discussed in case of polar molecule, so polarity is generally seen in heteroatomic molecules. Now you may ask me, alkane is a heteroatomic molecule constituted by carbon and hydrogen atom. The reason is the CH bond polarity is, in case of alkane molecules, is kind of ignored because the electronegativity difference between the carbon and hydrogen atom is very small. So it is less than 0.5. I'll explain in detail the latter part of my presentation. Now in case of non-polar molecule, there is equal sharing of electron pair. In case of molecules like hydrogen, oxygen, nitrogen and chlorine. Now in case of hydrogen molecule, you see equal sharing of one electron pair. In case of oxygen molecule, you will see there is equal sharing of two electron pair. In case of nitrogen molecule, you will find there is equal sharing of 3 electron pair between the atoms involved in the bond formation. So since the atoms involved in the molecule is the same, so non-polarity, as I already said, is seen in homoatomic molecules. So since the atoms are same, which are held together by covalent bond, electronegativity will be same, and therefore the electronegativity difference between the similar atoms will be 0. And therefore there will be no partial positive and negative charge. And in case of homoatomic molecules, in case of hydrogen, oxygen, nitrogen and chlorine molecule, you find bonds between identical atoms. And in case of non-polar molecules, there is even distribution of negatively charged electrons around the molecule, and this will lead to a symmetrical electron cloud. And you will not find any polarization of the electron cloud, or you will not find the electron density more towards the one side of the molecule. So the electron cloud is symmetrical, or to put it in simple terms, there is even distribution of negatively charged electrons in the non-polar molecule. And therefore you don't find any positive and negative end, and therefore non-polar molecules have a non-polar covalent bond, and the dipole moment will be 0. So dipole moment is a measure of polarity of a molecule, and is denoted by symbol mu. And dipole moment is a vector quantity. It has both the magnitude and direction. So here in case of non-polar molecules, dipole moment is 0 because there is no positive and negative end in the molecule. So one can predict polarity based on the electronegativity difference between the atoms held together by a covalent bond. So whenever the electronegativity difference is 0 or less than 0.5, you can take it for granted it will be a non-polar molecule, or the bond will be a non-polar covalent bond. So like I mentioned in case of alkane molecules. So though alkane molecules is constituted by two different atoms, carbon and hydrogen, it is non-polar in nature because the CH bond polarity in alkane molecules is kind of ignored because of the small electronegativity difference between the carbon and hydrogen atom. So let's see what happens in case of alkane molecule like methane. So electronegativity value of hydrogen is 2.1 and carbon is 2.5. So what is the electronegativity difference? So the electronegativity difference between carbon and hydrogen is 0.4, which is less than 0.5. And therefore, though the alkane molecule is constituted by two different atoms, carbon and hydrogen, because of the small difference in electronegativity, it is non-polar in nature. So in case of hydrogen molecule, both the atoms are similar. So when you do the simple max, 2.1 minus 2.1, you'll end up with 0. So in case of homoatomic molecules, you find bonding between identical atoms, and therefore the electronegativity difference will be 0. Now here are some additional details about the polar molecules. Now as I already explained, polar molecule has a partial positive and negative charges. So what we have discussed so far is in relation to a diatomic molecule. So diatomic molecule can be polar or non-polar. If it is homoatomic molecule, it will be non-polar. If it is heteroatomic molecule, it will be polar in nature. So what about triatomic molecules, where the molecule is constituted by three atoms? Now in case of triatomic molecule, you have a central atom. Now the central atom in case of triatomic molecule, in case of polar molecules, it has one or more lone pairs of electrons. So in case of triatomic molecule, if it has to be polar in nature, you find a lone pair on the central atom. In case of ammonia molecule, the central atom is nitrogen atom, which is covalently bonded to three terminal or outside hydrogen atoms. So you find lone pair of electron on the nitrogen atom in case of ammonia molecule. In case of water molecule, you find two lone pairs on the oxygen atom. In case of hydrogen sulfide, you find two lone pairs on the sulfur atom. In case of sulfur dioxide, you find two lone pairs of electrons on the sulfur atom. And though there is two lone pairs of electrons on the two terminal oxygen atoms, it doesn't make any difference. So all we need to know or we need to look at is the central atom. You just have a look at the central atom and see whether it has a lone pair or not. So if it has a lone pair, then definitely it will be a polar molecule. So if there is no lone pair in the central atom, then it will be a non-polar molecule. Now polar molecules like ammonia, alcohol and hydrogen chloride are soluble in polar solvents like water by means of hydrogen bonding. So what about non-polar molecules? Now non-polar molecules, they have no partial charges. The central atom has no lone pair of electrons. So I am talking in relation to a triatomic molecule. So in case of non-polar molecule, you will find that there is no lone pair on the central atom. In case of carbon dioxide, you find that the central atom is this carbon atom. It has no lone pair. So while the two terminal atoms, that is two oxygen atoms, it has two lone pairs. So it doesn't make any difference whether it has lone pair or not. That is terminal atoms. So all we need to look at is the central atom, whether it is bearing a lone pair or not. So in case of methane molecule, the central atom is carbon atom without a lone pair. And in case of boron trifluoride, the central atom is boron without any lone pair. So in case of non-polar molecule, the central atom has no lone pair of electrons. And in terms of solubility, non-polar molecules like naphthalene, alkanes, and lipids are soluble in non-polar solvents like benzene, hexene, cyclohexene, and carbon tetrachloride. That is by van der Waals forces or by means of van der Waals interaction. So there is a saying in chemistry, like dissolves like, and as it is rightly said, polar molecules dissolve in polar solvents, while non-polar molecules are soluble in non-polar solvents. So let me explain with suitable examples. Now, alcohol is a polar molecule. Now, alcohols are soluble in polar solvent like water, and it is hydrogen bonding between the alcohol and the water molecules that makes the alcohol soluble. So when you add alcohol to water, so remember water is a polar molecule with a positive end and a negative end. So when you add alcohol to water, it completely dissolves, you get a clear solution. So this is because of hydrogen bonding or hydrogen bonding interaction between the alcohol and the water molecule. Now whenever you find hydrogen bonding, you'll see that there is participation of hydrogen atom. So hydrogen atom that is covalently bonded to electronegative oxygen atom in the water molecule interacts with the electronegative oxygen atom of adjacent or nearby alcohol molecule. And what about non-polar molecules? So non-polar molecules like naphthalene, it is soluble in non-polar solvents like benzene. Now naphthalene is a aromatic hydrocarbon, and even benzene is also a aromatic hydrocarbon. So when you add naphthalene, which is a non-polar molecule, to benzene, which is also a non-polar molecule, you find that the naphthalene completely dissolves. You get a clear solution. So polar molecules are soluble in polar solvents, while non-polar molecules are soluble in non-polar solvents. Now polar alcohol molecules are soluble in polar water molecules by means of hydrogen bonding. So when you add alcohol to water, which is a polar solvent, you get a clear solution. It completely dissolves, solubilizes. And the reason behind the solubility of alcohol in water is the hydrogen bonding interaction between the alcohol molecules and the water molecules. So here you find the hydrogen bonding between the hydrogen atom of water molecule and the electronegative oxygen atom of alcohol molecule. So that is one way of looking at the hydrogen bonding between the alcohol and water molecules. The other way of looking at it is not only the hydrogen atom, even the oxygen atom, electronegative oxygen atom of water molecule can also participate in the hydrogen bonding. And the hydrogen atom of alcohol molecule will be at the receiving end. Because both alcohol and water molecules both have hydrogen atom that is covalently bonded to electronegative oxygen atom. So you'll find hydrogen bonding between not only between alcohol and water molecules, but also bonding between water molecules as well as alcohol molecules. So polar alcohol molecules, glucose molecules and ionic sodium chloride dissolve in polar solvent that is water. And what about the solubility of non-polar aromatic hydrocarbons like naphthalene? Now non-polar aromatic hydrocarbon like naphthalene dissolves in non-polar solvent like benzene, which is also aromatic hydrocarbon. And this is due to van der Waals interaction between or van der Waals forces between naphthalene and benzene. So it is because of the van der Waals interaction between the naphthalene and benzene that makes the naphthalene molecule to completely solubilize or dissolve in non-polar benzene solvent. So let's see how this actually happens. So benzene is a liquid while naphthalene is a solid. So naphthalene is a crystalline white solid with a melting point of 80 degree Celsius. And you may ask me, how come that naphthalene, being non-polar in nature, is existing as a crystalline solid with melting point around 80 degrees Celsius? The reason is van der Waals forces. So when you add naphthalene to the benzene, liquid benzene, you will find that on slight stirring, the naphthalene completely dissolves. You get a clear solution. Now, naphthalene molecules in the crystalline solid are held together by van der Waals forces. And that is the reason naphthalene exists as a crystalline solid with a melting point around 80 degree Celsius. So it is the van der Waals force between the non-polar naphthalene molecules that holds them together, and that is why it is crystalline and solid in nature. Now when you try and dissolve the solid crystalline naphthalene in benzene, so what happens is that the again the van der Waals forces comes into play. Now in the crystalline naphthalene, you find the van der Waals forces only between naphthalene molecules, and when you dissolve the solid naphthalene in liquid benzene, which is also aromatic hydrocarbon, you will find that new hydrocarbons, that is van der Waals forces, are coming into play between the naphthalene molecule and the benzene molecule. Remember, both are non-polar in nature, and same applies even for alkane molecules like hexane. So hexane is soluble in pentane, which is also a aliphatic hydrocarbon. So hexane is a aliphatic hydrocarbon and pentane is also a aliphatic hydrocarbon. So when you add hexane to pentane, it completely dissolves. That is, hexane completely dissolves in pentane, and this is due to van der Waals interaction. So non-polar hexane dissolves in non-polar pentane solvent due to van der Waals forces or due to van der Waals interaction between the pentane and the hexane molecules. So the crystalline nature of naphthalene is because of van der Waals force or interaction that holds the naphthalene molecules together, and it is the van der Waals force or interaction between the naphthalene and the benzene molecules that dissolves the naphthalene in benzene. And once again, it is the van der Waals forces which plays a vital role in dissolving the non-polar hexane in non-polar pentane solvent. So another question arises, how come benzene is liquid while naphthalene is solid? Because the size of the naphthalene molecule is bigger as compared to the benzene molecule. So benzene molecule is smaller while naphthalene molecule is bigger. So bigger the size of the molecule, more will be the van der Waals forces. And smaller the size, lesser will be the van der Waals forces. Don't forget to subscribe my channel, share, like, comment, and watch the full video. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.